I want to point out some differences between craters and calderas. And I'd like to start just by comparing Mount St. Helens on the left to Mount Mazama, which is the name of the volcano that erupted to form the modern day Crater Lake. And Mount St. Helens, the depression that you see at the top of that volcano is a crater. And it resulted from an explosion of the material out of the top of the volcano in 1980. And the result was that about a 1 mile diameter crater was created, and about 1,200 feet of the top of the volcano was removed during that eruption. Now, in contrast, a caldera is what the lake in Crater Lake fills. Even though it's called Crater Lake, it's actually filling a caldera. And the difference is in part size. So you'll see that the caldera at Crater Lake volcano is on the order of 5 miles in diameter. And during that eruption, the caldera forming eruption, the top of the volcano, about 5,000 feet was removed off the top of the volcano. So there's a very big size difference, and the mechanism that they form by is different too, because the calderas are a collapsed structure, whereas a crater results from just material being removed off the top of the volcano. So these differences also result from differences in the size of the eruption. And so, for example, these spheres are supposed to represent the relative size differences between eruptions that you probably have heard of, including Yellowstone, the Crater Lake eruption, Long Valley caldera, and I take students to Long Valley every other year or so in volcanology. Krakatoa. These eruptions and ones that are about VEI 6 or above. We haven't covered VEI, it's the Volcano Explosivity Index. We will do soon. But that size, and here we're talking 13 cubic kilometers to 20 cubic kilometers of material erupted or more, and that increases to this example of the Toba volcano, which exploded 2,800 cubic kilometers of material. Those size eruptions generally are an eruption of enough material that there's a void left underneath the volcano that the top of the volcano collapses into to create a caldera. The smaller eruptions that we see here, and those include the 1980 eruption of Mount St. Helens, 79 AD Vesuvius, that I'm sure you've heard of, Pinatubo in 1991, that there are a lot of videos about, this unpronounceable Icelandic volcano that erupted not too long ago. Those eruptions were not large enough to form a caldera, but rather craters form at the top of those volcanoes because of just the explosive removal of the top of the volcano. Now, a caldera forms when an erupting volcano empties a shallow level magma chamber. The top of the volcano collapses into the void that's left from that eruption, and it forms a steep bowl-shaped depression that's called a caldera, and that's derives from the Spanish word for kettle or cauldron. These features are variable in size. They range from about 1 kilometer to 100 kilometers in diameter. And in most cases, they can be differentiated from summit craters, which are generally much smaller and form by the explosive erosion of that central vent. And if we look at an example of what the caldera formation process might have been for Mount Mazama to form Crater Lake, what you see in the first diagram is a magma chamber with various conduits up to the surface and the beginnings of an explosive eruption. In the second image, we see that there's oh, excuse me, that's not the second. Let's try again. In the second image, we see the void that's left by the eruption. In the third image, we see the collapse of the top of the volcano into the void that's left. I mean, this is oversimplified, of course. In reality, this process is much less neat, I'm sure. But the overall concept is correct. And the collapse of that volcano, the top of that volcano, leaves this bowl-shaped caldera rim. And finally, these features are large enough that they may be filled by a lake, as in Crater Lake, which would more correctly be named Caldera Lake, or the lake that fills in Yellowstone National Park. So felsic calderas are surrounded by thick blankets of pumice that are derived from the eruption of large volumes of pyroclastic sheet flows. And there are variations in the form and the way that the calderas are created that we can divide them into three basic types. And those would be a crater lake type caldera that's associated with the collapse of a stratovolcano or a composite volcano, a basaltic caldera that would be associated with the summit collapse of shield volcano, like Haleakala in Maui, Hawaii, or a resurgent volcano, resurgent caldera that really lacks an association with a single centralized vent. If we look at just the formation of a crater lake type volcano, these kinds of calderas are associated with the collapse of the stratovolcanoes, where the top part of the volcano is blown up during an eruption, and the caldera forms in response to the removal of large volumes of magma from that shallow crustal magma reservoir. The basaltic calderas, like Haleakala, are forming in shield volcanoes and not the stratovolcano, the pointy peak stratovolcanoes. This is a picture of the caldera in Haleakala volcano on Maui, Hawaii, and you see cinder cones inside the caldera. The caldera is the bowl-shaped rim structure that you're seeing that doesn't quite fit into the field of view of this image. And then we have resurgent calderas like what we see in Yellowstone. And these start, we'll go through A through F here. Caldera formation begins with the uplift of the crust associated with the arrival of a large plume of gas-rich rhyolitic magma. The next stage would involve ring fractures, so these features here, propagating outward from the chamber and toward the surface. These are the conduits for the escaping magma. And then there's decompression of the magma that results in a massive vesiculation and an explosive eruption of tephra into the atmosphere. Next, we have the end of the eruption, when there are pyroclastic flows beginning to erupt from the ring fractures, represented here. The magma chamber is depleted, the crustal roof begins to collapse, and that generates additional pyroclastic flows. The next stage would be at the end of the eruption when there are hundreds of meters of pyroclastic flows that have accumulated within the caldera. Those are called the inflow facies. Outside of the caldera, those pyroclastic flow deposits are called the outflow facies. The next step involves the formation of a lake potentially in the floor of the caldera, and that's like Yellowstone or Crater Lake. And then finally, we have a resurgence of the caldera floor that might take 1,000 to 100,000 years to accomplish. And that period of uplift is controlled by the compression of the remaining magma beneath the collapsed roof of the chamber or by the arrival of new magma into that chamber. And just to compare the different sizes of eruptions that we've been talking about, we discussed a crater forming eruption like Mount St. Helens, and that size eruption, that amount of material that was erupted, is much smaller than the other volcanoes that produced calderas. Crater Lake had an eruption area quite a bit bigger, smaller than the eruption of the Bishop Tuff when the Long Valley caldera was formed. And all of those quite a bit smaller than the ash and other deposits that were erupted when Yellowstone caldera was formed.